All right, our next speaker is Professor Noelia Gutierrez from Carnegie Mellon, who will talk about machine learning for large-scale computational fluid dynamics simulations.
Hello, good afternoon, everyone. Thank you so much to the organizers for inviting me. So for those of you who don't know me, I'm Noelia. I'm at Carnegie Mellon University. I'm an assistant professor, and my lab works mostly on cardiovascular flow simulations. So we try to develop methods and apply methods that have the potential to improve patient care. So the main topics that we have, or main thrust in my group, are the use and development of computational simulations for patient risk stratification. Also creating new models that not only is for prediction, more like in a clinical oriented way, but to understand disease and maybe inform experimental studies that can help couple like this computational and experimental approach. And kind of like following the theme of the previous presentation, we are really interested in clinical translation. So all of us are aware of all the computational models and high-performance computing tools, but these are not yet a reality in the clinic. So we really want to move the needle in making these jump from just academic research to like something that can be used for patients. So, and this is kind of like motivating the idea of digital twins in healthcare. We have, a human, in this case, would be the physical entity, and then we have a virtual entity where we have our models, either physics-based or data-driven types of models. And the key part here, because this is not just a model, right? We want to have some data flow between the actual thing and the computer. And in healthcare, this is done through sensing. Like in this requires diagnostic testing tools, things like ultrasound. It can be like very advanced, or it can be some more ambulatory. And like today also, the use of wearable devices and how we incorporate that data into simulations is a new area that can help us make that connection. So we need really efficient ways of integrating all this data into the models so this becomes a reality. On the other side, we have the modeling. And as I just said, these models are not efficient enough as of today to be used in a clinical setting where the turnaround times are long, and we want to maintain the high accuracy, but we need to be able to make these decisions in minutes, not like days or longer. So towards this idea of digital twin, we have different projects in the lab that range from more patient-specific type of modeling, looking at cerebral blood flow, kind of like newer areas. For example, like we're trying to model blood flow in the placenta. We are trying to do multi-scale modeling in complex problems like thrombosis. But what I'm going to focus today is in our work more on the methods and like efficiency of these simulations, more in like a general way, not necessarily to one particular application, but just looking at how we can use machine learning models for CFD and how we couple these two. So this is the typical pipeline for some of the simulations that I work on. We do a lot of image-informed CFD, and this is an example of a coronary anatomy. So we want to simulate the flow in the coronary arteries and be able to predict whether someone may be at higher risk of developing a stroke, for example. So we do a direct segmentation of the image data, and that's going to give us our computational domain. And then we can generate a mesh, a finite element mesh in this case, and then we set all the boundary conditions. We choose how we're going to set up the simulation, and then we go into a high-performance computer and actually run the simulation. And these may take up from hours to days, depending on the resources that you have available to you. But this is not something practical for clinical applications. Now, there's always going to be a trade-off between how much resolution you can get in your simulation, like if you need to fully resolve all the flow details. For example, like if you want to resolve all the flow near the wall to get a good wall shear stress approximation, that computational cost is going to go up. And I plotted some examples of some of the simulations that we have in our lab, and you can see how as you keep increasing the number of elements, things go up and escalate pretty quickly. There are some strategies on how to reduce the computational cost that are physics-based. So you can play with different dimensionality using reduced order models. That is something that I've also worked on. So you can go, instead of having a full 3D model, you can simplify and then use a 1D model. Now, this is obviously going to simplify the physics, right? So you're going to miss information. In particular, if you're doing patient-specific, you're going to miss a lot of the information. So you can do an in-between and maybe do a hybrid combination, like some 3D in the areas that you're really interested in defining the flow, and combining that with reduced order models that provide more of the context. So you have kind of like a little bit of both. It still has a significant reduction in the computational cost. Now, there is still like some limitations. One is that you need to know a priori what is your region of interest. That may not always be the case. So for example, in this case, it's pretty obvious. If you have a stenotic region, that is probably where you want to focus your attention, but sometimes that not may be as straightforward. And also, you still have to do a computational simulation, and typically that region of interest is where more of the computational cost is going to be concentrated. So it can still be quite computationally expensive, and maybe you still need to use some resources that are not available in the clinical setting. So one thing that we started doing a few years ago when I joined CMU, because you're in CMU, right? Like machine learning is everywhere. So we started thinking about this idea of applying machine learning for super resolution. And the idea is pretty straightforward. It's basically the same as you would do for video or images, right? You have a highly pixelated or like low resolution image, and then you want to upsample using machine learning, and that typically yield better results than that using other upsampling methods. Now, one thing that we encountered when we started looking at this approach is that most of the studies we found at the time, typically the training was done on low-resolution data, but this data was created by downsampling the three-dimensional or high-resolution data. So that is not exactly the same, because when you are running a simulation with low resolution, you have all that numerical error that accumulates, and you're directly missing a lot of information. And that is not exactly what would happen with you downsample. So the first thing we did is to really create a database that we could use to be very sure that we have this low resolution by creating those low resolution meshes and high resolution data. So then we could use that to train our super resolution models. So we published this data set, and it's open. Everyone can download it and use it, which had like some external and internal flow conditions. We have all those pairs in like low resolution and high resolution data, so you can use that for multiple purposes that involve like training some type of super resolution algorithm. So how we approach our model is, first we decided to use graph neural networks. And that was not something that we've seen a lot. Most of the cases that we see, like we would use more like convolution neural networks in structure type of, more like pixel organization type of data sets. But our end goal was to use this for cardiovascular simulation. So we want to be able to deal with very complex geometries, such as the ones that we typically encounter when we try to mesh anatomies. And then having the graph neural network would allow us to map directly from the mesh into a graph with no loss of information. So we frame our model around the use of graph neural networks. So that was the first step, like to convert everything from traditional finite element mesh to a graph neural network. And then we started thinking, okay, now we have everything set up. We see like this loss of information. So can we recover the missing physics with our model? So that was the goal. So in order to do that, we need to think about what is lost here, what are the sources of error, and we know we have different types of error, round-off error, iterative error, but in this case, when you're comparing low and high resolution, your main source of error is discretization error. And we can describe that mathematically using, for example, a power series approximation. So we know this is going to depend on the mesh size. It's going to depend on the order of accuracy. So with all these, this means that the super resolution problem can be defined simply as some error added to the low resolution solution so you can recover that high resolution solution. So this is what we wanted our model to be trained on and to learn to do, to calibrate that error that is between the low resolution and the high resolution. So we developed this Taylor series error connection network, which basically is doing that. So for each center node, we average all the edge sizes, and that gives us some information about the characteristic edge size, so we can estimate what's going to be the error and then learn all the parameters during the training process. So this is how this network look like. So we have kind of like two main components. We have that TICNEC, that Taylor expansion correction error, is going to calibrate the error. And then we have the operator that's going to basically correct, based on that error, our low resolution input. So one of the advantages of using this type of approach, more based on the actual finite element data, is that we don't have those issues related with the solution diverging from when we move in time, because we always have an input that is physics-based. So the only thing we are doing is really reconstructing the high resolution. We are not generating new data, new information. So here's some examples. We observed that we were able to recover most of the high-resolution features. Around like 90% of those were recovered, and this got us as computational savings around like 42%. So that was very encouraging. Obviously, all of this was 2D. So we wanted to scale, and that came up with another set of problems, because now you start like entering the domain where the network may be at capacity and you cannot handle that much data. So, but we always kept in mind that what we really wanted to do is to be able to simulate this type of problem. So we need a system that is flexible, that can be generalized, and can also be scalable, because these models typically have several millions of elements, which is something that the network may not be able to handle as it is. So, we started thinking about this idea of the principle of locality. This is not something new, right? It's been known. So you know that when you have a physical system, the points that are closer together are more strongly coupled. And this concept has been used also in physics, but the idea of domain decomposition is broadly used in computational mechanics using physics-based models. So we wanted to couple kind of like these two concepts, the domain decomposition, the principle of locality. So that means that if we divide our domain into different sections, following the definition of the principle of locality, we know that there's going to be a region where most of the points that are surrounding like a specific point would be the ones affecting the outcome or the solution at that particular location. And so let's say we have a point X that belongs to our domain, and we can define this U where it's basically going to be an area around this point where we can consider as the locality, okay? So because we can define the function in that way, basically ignoring what is outside this locality, then we can also rewrite and formulate the neural operator to be acting on that locality too. So that's kind of the idea. And the main two takeaways that we got from this initial approach to just decompose the domain were that we see how we can, we see a linear increase as we increase the area, you will need to linearly increase the number of layers too. So there's going to be always a coupling between the number of layers you need in your network and that area. But also it is very important how you choose that area. Those windows that you define to partition your domain are going to be dependent on the frequency content of your solutions in those domains. So you can basically approximate the delta of that window by looking at how many points there are within that domain and what is the frequency associated with the solution, like for example, like a velocity solution in that particular domain, in order to choose the appropriate window. So what we wanted to do, so now we have a way of decomposing the domain, and we saw in this work, we saw in this work that we see increased performance, increased accuracy when we are solving just in that locality and then putting it all together than just applying the model to the full domain. So now we wanted to couple those two things. We have our super resolution algorithm, and then we also have a way to scale into bigger problems. So we wanted to try something more realistic, maybe a 3D problem. So again, now the idea is the same as what I explained earlier. So you would get the geometry, and then you would use a numerical solver, traditional solver, to create this low resolution that should be a pretty cheap simulation to run. And then with that, that would be your input to the super resolution algorithm that now you're going to partition in these different localities, and you're going to apply your model directly to each of those partitions, and then you're going to put it all together again. So I can show you some of the results we got with this example. So this is a low-pressure duct flow. This was from a project that we had a collaboration with the company. And here you can see how the low resolution misses a lot of the information. And this is the velocity. I will show you also the pressure is much more obvious because this is a Venturi duct. And we are able to recover most. If you look at the B and C sections, we are able to really recover. And now if you look at the cross section, the velocity, the high velocity in the Venturi is completely missed by the low resolution, but you're able to recover all that distribution of the velocity profile when you're applying this super resolution. Now this is the same location, the same duct, but now looking at the pressure. Again, as you can see, the low resolution completely misses what's happening in terms of the physics, but we are able to recover to pretty good agreement with the high resolution simulation by using the algorithm. And the best part of it is that the computational savings are very significant. Now we can see by splitting these domains, now you basically can parallelize your machine learning model, and you see up to 82% of computational cost reduction. So even if you, and here we are accounting for both the inference time and the machine learning model, but also the time that requires to run the low resolution solution. So both are included, and it still is about 80%. So now I want to show you a slightly different thing. It's kind of related. It's following this idea of partitioning the domain with this goal of scaling up what we can do with machine learning models. But I'm not going to talk about resolution, but more about surrogate modeling, but using machine learning. And the idea that we have is like, okay, now we can split the domain, and that means that this allows us to scale the problem and to use multiple GPUs. This is basically what we have been doing for CPU computing like for years, right? But we are using the same machine learning model that is trained in like a very general case, and we are using that for the full domain. But in some cases, we have a lot of differences, especially when we are looking at the flow of physics, in my case. So can we be a bit more specific? Can we be can we not only decompose, but do some kind of like a smart decomposing, where we are also characterizing the physics and training according to different physical features. So here we were working with some of the open data sets from the Johns Hopkins Turbulence Database. And in this example, you can see a transitional boundary layer, and there are kind of like 3 areas, very distinguished, where you can see different types of flow regimes. So what we see is that, or like what the intuition would tell us, is that if you use the same model for the full domain, it's probably going to do much worse than if you were to train specifically for this laminar part, or if you were to train specifically for the transitional part. And that is actually what we tried to prove here. So now let's say we pick a few samples. I put like 3 examples from like these different regions. And then what we're going to do first is we're going to do some feature encoding. So we can either look at principal component analysis, or we can look at their energy spectrum and look at the frequency content of each of that small domains. Now, once we do that classification, then we can cluster these different domains in groups by using either k-means or Wasserstein distance. And that is going to create like different model libraries that then we will use to train. So instead of training with just one model, now we have 2 or 3 different models that we use to train depending on the characteristics of that particular partition. Now, the other important thing is that we are splitting this domain, and we are applying this principle of locality and basically ignoring everything that's out there, but it's not really ignoring. Then we need to put it all back together. So in order to do that, we need to also handle how the boundary is encoded, so the model is aware that there is a boundary and there's going to be some information that's going to be shared among adjacent partitions. So we tested these in 2 operator regression models. So we were not developing a new model. We were more developing like a layer that would go on what is already out there. So we used the Fourier neural operator. More in particularly, we consider the boundary embedded, because we were really interested in considering that boundary effect. And then we use also the operator network deponent. So with these 2, basically, we apply this training done with these different model libraries, and then we do the inference also, where the data goes in, it's classified, and based on the type of data, the types of features that are observed in the flow, then it would go to one of the models from the model library. So I can show you some of our results. We just submitted these recently. So here's where you can see an example. This is for time 0, and I will show you also how this does also in time. So you have the prediction, the ground truth, error, and you can also see the different partitions that are created. So how the model automatically distributes those different domains into those 3 different groups. So we were using 3 models. I can show you also some data about how we came to these 2-3 model partition. So as you can see, the results are pretty good. Like if you look at the prediction and ground truth, you can barely tell, and the errors are very contained and very small. So this was very encouraging. So we also did a lot of analysis of what was better in terms to classify the physics, and also whether there was a difference between using 1, 2, 3 different types of models when we were classifying the physics. So in general, we found that using this energy spectrum and mostly Wasserstein distance tended to be the combination that would better cluster these different physical features. But we also found that depends maybe a little bit also on what type of model you are using, because we saw different results when we were using the Fourier neural operator or when we were using the PONET. In general, also, we observed that using more than one model was usually yielding a better accuracy in terms of R-square. We also have another example that I did not include here, but it is also important to consider how much variability in the physics dynamics may be in your problem, because it's not always going to be just 2 is the perfect number of partitions or 3. So ideally, you want to let the model explore and then make a choice of how many partitions you may want to be using. So to summarize, we presented this super resolution TICnet, which is able to achieve up to 90% of accuracy compared to the high resolution, while it's accounting for 40% less of the computational cost. We saw that imposing this locality and force decomposition is able to improve prediction accuracy. And in general, physics characterization improves training and inference when we are using that with different types of operator regression models. We observed that Wasserstein distance and energy spectrum optimally classifies the physics dynamics. That was for the problems at least we were exploring, but this may be slightly different if there are different flow dynamics. And now, with these and with the models that we tested, we are able to use these machine learning models in sample size in computational domains that are about 6 million elements. And I say large here, and I know this is a very subjective term. For us, 6 million elements is kind of like in the bulk part of what we would typically use for our simulations. So we think like this is something that I guess at least works for us. But this can be further scaled, because the scaling that we have seen, it seems like it would allow adding more GPUs in parallel. So there is really, as long as you have access to the hardware. So I would like to thank my students and my collaborators, and I'm happy to take any questions. Thank you.
Thank you, Noelia. We have time for one question. There's one question in the back.
Yeah, thank you for a nice presentation. How are you applying or imposing the boundary condition at different domain, having different following different physics, and how are you ensuring the consistency of the boundary, what you are applying?
Yeah, so what we are doing right now, and this is still work in progress, as actually that is kind of like our active area of research, how we handle the boundary better. So we are imposing boundary awareness when we do the decomposition, so the model knows that there is a boundary. And then when we are putting everything together, we are not enforcing continuity, but we are not enforcing like same solution at the nodes, but we are averaging. So that is not an ideal, that is a temporary solution. So what we want to do now is to explore more ways of how we can, do more communication of the boundaries as we are doing the inference. So this process is a bit more straightforward. But the boundaries are aware that they're like what models may be connected to them. So that's something that we can include.
All right. Thank you very much, Noelia. Let's thank our speaker once again.